Rules of differentiation. All right, we have what's called the constant rule. Let's say if C is a real number, then the derivative of any constant called C. So d over dx, that's one way, right? We can say derivative of just C. Think about what derivative means again. Remember we did that little word cloud last time and everybody put something, then I said by the end of class, everybody's gonna be saying the same definition of the derivative pretty much. Slope of the tangent line, right? So if you have an equation of a constant y equals 5, y equals -2, y equals 0, y equals, I don't care what the number is, it's just a constant. The graph all looks similar, right? It's a flat line, right? So what's the slope of a flat line? 0. So the derivative of a constant is always 0. So example, f of x is equal to 5, slope of the tangent line of a horizontal line is always 0, right? You can see that picture if you want. Slope is 0. All right, the next rule is probably the most useful rule in calculus as far as taking derivatives. It's called the power rule. And we're going to start off using our exponents to be positive integers only right now. It applies later on to negatives and fractionals and stuff like that, but we'll keep it positive. We'll get to those later. So if m is a positive integer, such as 1, 2, 3, 4, 5, 6, 7, blah, 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 going on and on, right? Then the derivative of some variable to that m power is equal to the power multiplied to that variable, now to the 1 less power, m minus 1. So if I have f of x is equal to, let's just put x to the 7th power, f prime of x, this derivative, is using this power rule. The power comes out to the front as a factor, 7, multiplied back to the variable, to the 1 less power, 7 minus 1 is 6. That's the derivative. Now you could do the long formal way. I'll show you that real quick and see how long it takes to get to 7x to the 6th doing the long formal way. Formal way is the limit as x approaches 0 of f of x plus h minus f of x all over h, right? And so we do all this. F of x plus h, that's x plus h to the 7th power, minus f of x, x to the 7th, all over h. And now what we do. We have to sit here. X plus h times x plus h times x plus h. Do that 7 factors of x plus h. You can do the binomial expansion from here if you wanted to, if you remember that from pre-calculus. Might be able to do it quicker, but it's still gonna be a mess, right? So we can have blah, 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 minus x to the 7th, right? still all over h. Some things up here are going to factor, some things are going to cancel. H goes to 0, and that magically is just going to be 7x to the 6. So I'm saying now we got some rules, some tips and techniques so we don't have to go through all this, especially when those exponents become rather large. Now, if I could have demonstrated this with like an x squared, it would have been manageable, even x cubed, right? But when you get high exponents like that, we'll be here all day trying to figure that out. And there most likely will be some kind of careless error somewhere, right? Where just by looking at this, take the exponent, multiply it to the front, keep the variable, and the variable's power goes down by 1. That's the rule. All right. Constant multiple rule is an extension to that power rule. It's really the same exact rule because if I look at this x to the 7th up here, what's the coefficient? It's 1. I'm doing the same exact thing. Now I just put a number other than 1. I put a coefficient in front of the variable, and you do the same rule. So it's if f is differentiable at x and c is a constant, then the derivative, so d over dx of some constant times the function is the constant times c prime of x. It's just a formal notation for it, so you'll see it much clearer with an example with numbers. If I say find the derivative of negative 7/8 x to the 11th, this is negative 7/8 times the derivative of x to the 11th. Now, again, you don't have to go through all these steps. This is just really showing step by step how this rule works. This is negative 7/8 times derivative of x to the 11th is 11x to the 10th. Right? And now you can take these two constants and multiply them together gives negative 77/8 times x to the 10th. So you see how you can just take the 11 and multiply it by the negative 7/8 at the beginning, get your coefficient, new coefficient. Right. Keep the variable, reduce the exponent by 1. Let's say if f of x is equal to 3/8 times the square root of x, what is x f prime? If you recall, last time we did the derivative of the square root of x, we did it a long way, right? And I said it might be a good idea to remember that, right? You remember what the derivative of the square root of x was? Yeah, that's not the derivative, that's a rewrite of it, but 1 over 2 square roots of x, right? So you'll see that come up a lot. So that's why I said, maybe we'll just keep it in memory instead of having to derive it all the time, but you can still derive it, okay? The long way, and then we'll see another shortcut in a second. But I keep the coefficient of the 3/8, and I take derivative of the x square root of x we just said is 1 over 2 square roots of x, and we could simplify this. That's 3 over 16 square root of x. So this is the fun part of calculus. This is just the easy tricks and techniques, okay? It's more algebraic in a sense. There's not a whole lot of theory behind it just yet. We kind of did the theory part to understand what derivative meant. Now we know that, we can go straight to the shortcuts to do the calculations. All right, the sum rule. And it also applies to the difference as well, but then you call it a sum because you write a difference as the sum of two other numbers adding its opposite, right? So if f and g are differentiable at x, and the derivative of f plus g is nothing more than the derivative of f plus the derivative of g. So you put a minus in there too if you want to. And applies to that as well. So it's like polynomials. You take each individual term in the polynomial and take their derivatives and add them together. So take the derivative with respect to, say, w instead as our variable of 2w cubed plus 9w squared minus 6w plus 9. So it just uses that constant multiple rule, that extension of the power rule on every single term, as long as it's a polynomial like this. Yeah. Let's put in here for polynomials. Because later on, we're going to see some functions that are not polynomials. A polynomial divided by a polynomial is a rational function. We can't use this rule. Yeah. Polynomial times another polynomial. Now, we might be able to multiply it out and get one full expression as a polynomial, but you can't just take each individual term in every polynomial and take their derivatives, and that's not the answer. There's another rule for that. We're going to see those today. So derivative of polynomial is just the derivative of the 2w cubed, which would be what? 6w to the second, right? We multiply power times coefficient, 6, keep the exponent, and keep the variable, reduce the exponent by 1. Now the next one would be 18w to the first power. This is a 1 right there, right? 1 times negative 6, keep the w, and now the w goes to a 0, right? And then derivative of a constant is 0. Now we're going to simplify that further. What is w to the 0 power? That's always 1. Anything to the 0 is always 1, right? And then 0. So that's it right there. Simplifies to 3 terms. That's your derivative. All right, so this textbook is called Calculus with Early Transcendentals, right? So that means we're going to see some of the logarithms and natural logs, those kinds of expressions, trig functions, those things mixed in the beginning of the course. So the next one is derivatives of the natural exponential function. All right, since the number e is equal to 2.71828 ... right? It goes on forever and satisfies the limit as h goes to 0 of e to the h minus 1 all over h equals 1. Okay. This you can verify in the calculator if you wish. Okay, h is extremely tiny. Watch, I'll just put a very small number in there. And let's evaluate it out. So I have e to the tiny number minus 1. So let's do 0.001. That's good, right? Minus 1. Then divide by that 0.001. That's what h is. And you can see how that is not going towards 1. What did I do here? Limit as h goes to 0, divided by h. Oh, that's supposed to be a minus 1 outside the exponent. I copied that wrong. Let's see where it's at. There we go. So we got e to the small number minus the 1, then divide by 0.001. There you can see, very close to 1, right? You can pick a number smaller, smaller, you can make that conjecture. Okay, so that's true. All right, so the natural number function f of x equals e to the x. Natural exponential. All right, let's find the derivative of this. The derivative with respect to x of e to the x is equal to. Now I can't use a power rule on this because we said the exponents for that power rule need to be integers, like numbers, right? Our variable here isn't in the exponent, so we don't know what that is. So it's not an integer perhaps, right? So we can't use that. Our base right here is a constant, right? 2.718, blah, 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 blah. All right, so it's the exponential function. All right, so we're going to do the limit as h goes to 0 of e to the x plus h minus e to the x, that's f of the x plus h minus f of the x, all divided by h. All right, I'm going to break this apart. There's a rule that says adding your exponents. What did you do? Multiplied my bases, like x squared times x to the 5th is x to the 2 plus 7, right? Now I'm going to go backwards. I'm just going to say, instead of e to the x plus h, this is going to be e to the x times e to the h. Notice in the numerator, there's an e to the x in common, right? Let's factor that out. So that leaves e to the x times e to the h. E to the x times minus 1 is negative e to the x all over h. And if you remember your limit properties, the limit of, say, a product is the product of the limits. We can split this up into multiple limits. So look right here, I'm just going to split this up into a product of this fraction, like that, and that fraction. So we have the limit as h goes to 0 of the e to the x multiplied to the limit as h goes to 0 of the e to the h minus the 1 over the h. And we already know from what I just proved to you earlier, it really wasn't a proof, but we assumed it to be. It was told to us that this right here is equal to 1, right? So now we're just looking at the limit as h goes to 0 of e to the x. But what is h? They don't have an h. So this is the function itself, which is e to the x right there. So that's your derivative of e to the x. The derivative of e to the x is e to the x, the same exact thing. This is one of the easiest derivatives to take, right? Now it can get a little bit more complicated than just e to the x. It might be e to the 2x. It might be 5e to the 5x plus 7, something like that. We can make it more complicated, but you got the basics. E to the x is its derivative is just e to the x. So we'll expand upon that later on, but we have given f of x is equal to 2x minus 1/2 e to the x. F prime of x equals what? Very simple. It's in that polynomial format, right? Term plus or minus term, you can do that. So I'm going to take derivative of the first minus that derivative of the second term. That's your derivative. So what is derivative of 2x? Just 2. Think about it, if it's x to the first power, throw away the x. And it's just the coefficient that's left over, 2. And derivative of minus 1/2 e to the x. Minus 1/2 e to the x. That's it. That's your derivative. Very simple. What if I say, what is the equation of the line that is tangent to the graph of f of x at 0, negative 1/2. We need a point and a slope, right? Got the point. Where do I get the slope? From f prime of x, right? What number do I plug in? Evaluate f prime when x is 0, right? Because they share the same ordered pair. So we're looking at the slope of the tangent line at x equals 0, right? So 0, negative 1/2 is on that straight line. 0, negative 1/2 is on this curvy line, f of x. So this will give us our slope of the tangent line. So all I do is put f prime at 0 is equal to 2 minus 1/2 e to the 0 power. That's really nice. 2 minus 1/2, 4/2 minus 1/2 is 3/2. So that's our slope of the tangent line at 0. So we could use y equals mx plus b. We have a x and a y up here. Y is negative 1/2. Slope 3/2. x is 0. Therefore, your b is negative 1/2. The simple your equation is y is equal to m 3x times any x plus the b, so minus 1/2. Just graph both of them on here just so you can see how that works. F of x was 2x minus 1/2, I'll just put 0.5 e to the x. And then the tangent line at x equals 0 is given by this equation, y equals 3/2, so that's 1.5, right? Oh. X minus 0.5. You can put it in the fractions if you wish. I just think the decimals is sometimes easier to type in. It's all in one line. And let me just do zoom option 6, put it on standard window for now. I don't know what window I had last, but standards usually work. So that's f of x. And there is your line. You see they're touching it right there, right? At one point. Zoom in on it. A little bit easier to see here. So that's when x is equal to 0, right there. Your slope of that tangent line is 3/2. So that's an instantaneous rate of change. You want to say, okay, so I have a, I don't know, some kind of roller coaster modeling the speed or something over a given time period or whatever, where you can look at it and say, okay, how is it changing? Right when I say hit the radar gun at this point, at x is 0, it's changing 3/2, whatever units that may mean. Okay. 3 miles per hour. Oh, 3 miles in 2 hours. I don't know, something. But that's the rate of change right here. And you can tell over here when you get past, I don't know what this number is, it's probably 1.5 or something for x. It turns around, right? My rate of change is 0 right there, right? Slope of the tangent line is 0 at that maximum point. All right, so that just led into this question. Find points on the graph. Of f of x, where the tangent line is horizontal. So the tangent line is horizontal. That means it is equal to, slope of the tangent line is equal to the value 0, right? Horizontal lines have slope 0. So I want to find out where is this, right? It's somewhere in here, right? But I can't just look at a graph and say exactly where that is, right? I have to do some arithmetic, some algebra in this case. So this is where f prime of x equals 0, right? Now f at 0, x is not 0. The slope of the tangent line, its output is 0. It's flat. So I graph this like that. This was our tangent. We're looking for somewhere right here, right? Put it in blue. What x value? Well, if I set the derivative equal to 0, right? So f prime of x equals 0, which is f prime of x is 2 minus 1/2 e to the x. have to do a little algebra. This is college algebra right here. So if I add 1/2 e to the x, that's equal to 2. Multiply both sides by 2. Now I have e to the x is equal to 4. Now I say, what e to what power is 4? I don't know. So I have to introduce logarithms, right? Or rewrite this in its log form. This is natural log of e to the x can be equal to the natural log of 4 if you want to do that. Natural log both sides. X will come to the front using properties of logarithms. Natural log of e is equal to, it's just equal to 1. So x is equal to the natural log of 4, which you put in that calculator and see is your approximation. 1.386. Now, if I want to know, okay, so that's at x, what is its y value? So let's say, what is the ordered pair of this point? Well, it's going to be 1.386 comma something, right? How do I find the y value? With any function. Plug it in. If I have the x, x generates all the y's, right? So all I gotta do is evaluate f of the natural log of 4. The original function was 2 times x, so 2 ln of 4 minus 1/2 e to the ln of 4. And that gives you 0.773. Our ordered pair, 1.386 comma 0.773. Yeah.
And that point is on the original graph. Right?
On the original graph, yes.
Right. And so we were on the first part, we were using the derivative to determine that point.
At 0. Yes, at 0. So if we look back at this graph, see, this is the tangent line at 0, right? Right there. We're trying to find the tangent line at this point right there, and we want to know, what is that point? Well, that's what the derivative is equal to 0, right? So this occurs. Now I can actually let the calculator find this high point up here. That's a maximum, right? So calculator can do that. Second and trace brings you to the calculate menu. I'm gonna find the maximum on that graph. So option 4. I'm gonna move my cursor towards that maximum, but don't go all the way to the top. I want to stay to the left of it. So we just mark it. Now it says right bound. Now go over it. It's where I'm to the right of it. Enter, and I take a guess, and you can see that's gonna be the ordered pair that we just calculated out. Yep. So we'll do a lot of applications of this, trying to figure out where is the slope of the tangent line equal to 0. That has important things, right? Because the rate of change is changing right there, right? It is going in as usually the opposite direction, going from positive to negative or negative to positive, right? All right, so same kind of question, but now I'm just saying, okay, where is the slope 6? Now you guys do this one. So the first thing you always do, if you don't know where to start, remember I said take the derivative, obviously, right? And then the derivative's value is the slope of the tangent line will be 6. Solve for x. And so I'll give you a minute to do this. All right, so first thing, find the derivative. Power rule from each term, right? So it's 3 times the 2 makes 6. Keep the variable x, reduce the exponent to 2. Next, 2 times the negative 15 is negative 30. X, reduce the variable, so exponent to 1. And then plus the 24, right? So that's your derivative. Slope of the tangent line is equal to 6. So this is equal to 6, right? Notice I can divide everything out by 6, right? So everything divided by 6 can simplify this down to just x squared minus 5x plus 4 is equal to 1. It's quadratic. We need to solve quadratic equations by a few different methods. Factoring, if it's set equal to 0, quadratic formula, if it's set equal to 0, square root method, we can't have that x of the first term right there, that doesn't work, right? Do completing the square, nobody wants to do that, right? But the only way we can see is just to subtract off the 1, right? And set it equal to 0. So that's going to be plus 3. All right, so from here, we cross our fingers and hope that it can factor, right? Because it'll make life so much easier. With factors of 3, either add or subtract will never give you a 5, right? So we're forced to say no solution? No, that doesn't mean no solution. It just means it's not factorable, right? So it's not nice answers, nice rational numbers that we're looking at for answers. So we have to use quadratic formula. So hopefully this kind of brings back a lot of memories, hopefully not bad ones. X is equal to, you have to sing it, right? You get put to the tune, Pop Goes the Weasel. I'm not singing it, believe me, I'm having this recorded. No, I'm gonna get so many hate mail and stuff like that if other people hear this, no. All right, opposite of b, plus or minus the square root of b squared minus 4ac all over 2a, right? All right, it's already set up for your a is equal to 1, b is equal to -5, and c is equal to 3, standard form, right? Opposite of the b, opposite of -5. So just do the easy arithmetic by hand. You don't want to go straight into the calculator doing all this, right? Simplify as much as you could before having to go in the calculator. So b, -5 all squared minus 4 times 1 times 3 all over 2 times 1. Now we'll clean this up some. This is 5 plus or minus the square root. This is 25 minus 12, right? Makes 13 all over 2. That's the exact answers for x. That doesn't really tell me a whole lot, right? So I would put this in a calculator and approximate them. 5 plus the square root of 13, what's that, 3 point something something, all divided by 2, so 8 point something something divided by 2 is 4.3. I just did that in my head. No, I didn't. I have the answer written down, so obviously use the calculator, figure that out, right? And then the other one, 5 minus the square root of 3, all divided by 2, that one is 0.7. So at these x values on the graph, whatever that graph looks like is curvy, right? The slope of the tangent line is equal to 6. So I'll give you a quick sketch of it instead of just going to the calculator, because we'd have to probably zoom in and out a lot to see these. But this is the basic sketch of it. Polynomial function, so you know, so it looks like a roller coaster, right? Of 3rd degree means like that, perhaps, right? We're looking at slope of 6, so positive slopes, so 0.7 right there has a slope of 6. And at 4.3, that's this one over here. Actually, a little bit further. Right there, perhaps. It's going to be parallel, right? To this one. So this red line and the next red line I draw are parallel lines. Same slope. So you can kind of see where calculus can really be used in some real applications. You want to see if there's some rate of change that's happening along some, I don't know, some type of equipment. Maybe at certain times it speeds up, some certain times it slows down, and you need to figure out exactly where those times are. And you say, I want to know if it's doing 500 revolutions per minute, when? Well, if you know how that machine has a function to it or something like that, you can do the calculus behind it and do derivative, set it equal to that, and blah, blah, blah. You can say it happens here, it happens here, it happens here, and so forth. All right, we have also what's called higher order derivatives. We're still in the same section. These are derivatives of derivatives of derivatives of derivatives of derivatives of derivatives, and just keep on going on as long as you want, right? So you find derivative, take it again. Take it again if you want. Take it again, keep on going, right? So derivative of f prime this is called the first derivative, f prime, right? Is f double prime, second derivative. Try to think what this means. The first derivative is a rate of change, right? Now I take the derivative of a rate of change, which is a rate of change. So this is the rate of change of a rate of change. Go to the third, the rate of change of a rate of change of a rate of change. That's kind of mind-boggling, right? But the second derivative might be something to understand. We're actually going to do that later on. I want to see how fast is this change changing? Is it going slow or is it really changing quickly? It's like putting your foot on the accelerator. If you need to get to 60 miles an hour, there's several ways to get to 60 miles an hour, right? You can just push it very slowly, and the person behind you is honking the horn and saying, get out of my way, right? Or you can drive very aggressively and just stomp on it and get to 60 miles an hour quicker. So your foot is the second derivative. You want to think about how much force you're pushing on the gas pedal, right? The first derivative is just getting to 60 miles an hour. All right, so if I want to go even further, so f prime can go to f double prime, can go to f triple prime, the third derivative, and so forth, which we now say all the way to, we'll put an n like that. Usually in parentheses, it doesn't have to be in parentheses, but it kind of distinguishes from being an exponent. That just means this is the nth derivative. So these are pretty easy to do. Eventually, you'll see what happens to a lot of them. Let's say if f of x is equal to 3x cubed minus 5x plus 12. Let's find the fifth derivative. I'm going to go taking 5 derivatives. First one, second one, third one, fourth, and all the way to the fifth. Especially if they're polynomials, they're fairly easy. Just always using that constant multiple rule. Constant power rule, I should say. All right, so the first derivative, 3x cubed, that's derivative is 9x squared. And then minus the 5x to the 0, which is just minus 5. Derivative of the 12 is 0. It's constant, throw that away. F double prime. Now look at the first derivative and take its derivative. That's going to be 18x, and derivative of the 5, 0. Third derivative, derivative of 18x, 18. Fourth derivative, derivative of 18, 0. So anything beyond the fourth derivative is always still going to always be what? 0, because derivative of 0, 0 is a constant, right, is 0. So anything after the fourth and beyond, always 0 for this particular one. So notice how the terms get shorter and shorter, less terms in your following derivatives of polynomials, right? All right, what is the find? Let's do, I'm gonna put it in this notation so you might see. It's supposed to be our x. Find the 10th derivative. That's what that notation means, right? Of the function f with respect to the variable x. Another notation, right? All right, so this is the first derivative, right? It's going to be equal to just a 3. And derivative of 2e to the x is 2e to the x, right? That's first derivative. Now second derivative. Derivative of the 3, 0. And derivative of 2e to the x, 2e to the x. What about third derivative? Derivative of 2e to the x is 2e to the x. I could have said, what is the derivative of the 100th? The 100th derivative of f, right? You can see where it's going to, right? Because each time I keep on taking derivative after the third derivative, it's always 2e to the x. So this is just 2e to the x. So for the most part, if they're polynomials, a lot of times you can eventually come down to where the derivative is equal to 0, and then everything after that's all 0. You've probably derivated it out. That's how you say that. All right. Any questions? Speak now, forever hold your peace, because this is like critical. Big stuff going on right now today. Power rules. Yes.
Why don't we get rid of the 2?
Don't get rid of the 2 because it's still a constant. So you got a constant times your function, right? So the derivative of that is just c times f prime of x. So it's kind of same idea of the power rule in a sense, how that exponent comes out and multiplies to that coefficient is similar to that. You still always are keeping that coefficient. So the power rule, if I had like 3x to the fourth, this is 4 times the 3 times x to the new power of 3. And so it's still always there. So, but again, don't mix up e to the x with the power rule, because even though it looks like it's an exponent, you can do that. You can't do it with that one. We know derivative of e to the x is still always just e to the x. And you see it also when we get to other logarithmic problems or other base or exponentials where we got like 7 to the x power. There's a little tweak to that. Similar, but not